Hey, so my name is DeGrasse. I work at NXP Semiconductors as a contributor and upstream maintainer to Zephyr, and this is a talk on a proposal for a way to do clock management in Zephyr RTOS. So we're going to first discuss kind of the current clock control framework. We're going to look at what you can do and, frankly, what I think is a pretty good implementation of clock control in its current form. From there, we're going to discuss requirements for a framework if we were to rework this clock control system, at least from my point of view. Obviously, at the end, I think we'll probably have time for discussion to mention other use cases I might not cover here. And then I'm going to go over a proposed implementation for this, and then some implementation details beyond that. I'm going to try and leave some time at the end for discussion, because hopefully there will be some. I know this is a problem we all have to solve, right? We all have clocks. So first, just an overview of what we have right now in the clock control framework. So this framework has been around since, as far as I know, this goes long before me and Zephyr, I think since the beginning. And it's based around the idea of hardware-specific subsystems. These subsystems are effectively an opaque pointer that you pass through from your clock consumer down to your clock driver. So what do we support? We support the ability to get a clock frequency as an integer. It's very straightforward, just getting the frequency in hertz. You can set a rate. It's worth noting that's also the opaque parameter, so there's no guarantees there. That's an integer. You can get the status of a clock. You can gate and enable it, optionally asynchronously. And then you can configure a clock via an opaque pointer, which is kind of a catch-all method of doing additional settings with clocks. Besides reading rates, though, all data is kind of driver-specific, so there's not as much enforcement here. Drivers can then also read clock settings from device tree to set up clocks at boot time. You'll see this being done a lot for root clock sources, things like PLLs being read from some sort of device tree configuration. And then if you want to, again, the configure API is kind of a catch-all. You can shim a lot of stuff in here to accomplish a lot of different configurations with clocks right now. So now let's look at a usage example. I wanted to highlight ST here. I work for NXP, but I'll be frank, I think ST did a good job. The clock drivers, well done. There's a lot of functionality here. There's, and Erwin, correct me if I say something wrong, or make a face at me if I say something wrong, but there are SOC-specific clock drivers that implement functionality for each, as far as I can tell, series, and then there's these macros. So STM32GT clocks, what does that do? It sets up configuration data for the clock based off what's present in the device tree, based off these specifiers. So you have this clock node in the device tree, and then these specifiers, and this macro extracts that data, packages it up in a way that the STM clock driver will understand, and then you can pass it through with this clock configure API. So we have the ability to do things like enable or configure clocks, and that is all device-specific data. Things like register offsets and bits are being encoded by this macro. Beyond that, the implementation that ST has lets you do things like multiplexer selections. There's this driver for clock mux compatible that can apply selections at boot time for clock muxes. So you've got access to muxes here. The root clocks, things like PLLs, can be set up from device tree properties on the reset and clock controller node that ST has. So effectively here, you've got the ability to configure your root clocks. You've got the ability to configure your muxes. You can gate and negate. There's a lot available here, to be frank. But what isn't here, and what do we have issues with? So one thing here is code reuse. Fundamentally, things like dividers and multiplexers are going to get reused across SOCs. Things like PLLs, not so much. PLLs are IP that's going to change when you change your process node, things like that, and you can't always reuse them. They may have vendor-specific features on each implementation, but dividers and multiplexers, they divide, they multiply. There's not that many ways to do it, and they're going to get reused. We should reuse them. Additionally, runtime clock configuration is kind of limited with what we have now. You have the ability to gate, ungate, but more complicated stuff like PLLs. Again, there's that configure API, but at some point, there's problems. If you're trying to pack an entire PLL configuration into that pointer and you have one function implementation to do it with for your entire clock driver, you can run into issues, especially with optimization if you have a big switch statement or something like that to handle all that code. There's also not really anything for callbacks. It's worth noting there is, on and off callbacks, but there's no callback for, hey, someone else just reconfigured a root clock, that affects you. So if you're a consumer, you're not aware if somebody touches a clock that you're interested in, or rather a root clock that you're interested in because you are a descendant of that clock. Your node is that you're interested in. Additionally, clock control framework, it leaks device-specific data. So right, ST has this macro, this ST DT clocks macro, which works well for their drivers. And theoretically, we could all do that. We could all have our macro that does this, but what about designware drivers? Those aren't vendor specific. And there's also the fact that even if we did do a totally generic macro, you're still looking at issues like clock callbacks not being available in the framework right now. Additionally, the set rate API, I'll be honest, I kind of have a bone to pick with this one on embedded devices. We'll go into the proposal later, but not everybody wants the overhead of saying, give me clock frequency X and figure out how best to do it. That's an expensive operation to do on a low power device. And currently we have that opaque pointer for it, but that just introduces new problems because we're leaking device-specific driver, to be clear, clock driver-specific data out into consumers. So now let's talk about the requirements if we're going to rework clock control and try to implement something new and a little bit more capable. So just an overview of kind of the clock hardware that we all have and love. And this is the only photo I believe I have in the entire presentation because graphics are hard to find for clocks. So I apologize. It's dense. This is just part of the clock tree of one of the LPC series SOCs. So you have gates, often per peripheral. Additionally, you can sometimes gate root clock sources. And then sources themselves, you can sometimes power them off at runtime to save power. Beyond that, you have kind of dividers and multipliers, very standard, just divide a clock, multiply it. And you have multiplexers, so the ability to select from a different set of sources to then clock a given output. PLLs are also worth highlighting here because a lot of the stuff that I just mentioned is kind of generic. Sources, there's a gate bit or something like that. Dividers, again, there's only so many ways you can divide a clock. Multiplexers, it's usually just a setting and a register that corresponds to each input. But PLLs can have all these different settings. They're very much specific to each vendor. And as I mentioned earlier with code reuse, that's something that's a challenge for clock control drivers is how do you effectively do code reuse if you have a basically SOC-specific PLL in every SOC. Additionally, PLLs are something that kind of brings us into power usage because if you really want good power consumption, you've got to power down things like PLLs for low power modes. So then framework goals. First and foremost, we need feature parity with clock control. This is an API that's been around since 1.0. We can't just tell developers, hey, sorry, we're getting rid of this functionality that you needed for your application. We need to have a path forwards for them. Beyond that, we want the ability to configure clock settings at runtime. We want the ability to say transition from a high power set of clocks to a low power set of clocks and support powering off clock sources, saying this PLL is no longer used, we're going to turn it off, things like that. We want the ability to notify clock consumers when a parent changes rate. So we want, for example, if you have a clock tree with a PLL at the root and you change your PLL's output frequency, we want to be able to propagate a notification down to consumers saying the rate has changed, adapt to that. We also would like to describe clock hierarchy and device tree. I'll get to why I feel this is useful later and the implementation benefit it brings us, but initially I think the value here is that it makes it much easier to understand what's going on if you have things in device tree, if you have nodes for different clocks. From there, we want to maximize code reuse. So I mentioned earlier, digital IP, stuff like that, things that are not going to be reworked for every SOC. We want to be able to reuse that even if we need a custom driver for each PLL. And we want to minimize flash and RAM footprint. This one is really important to me because this isn't something that is optional. Clocks are always on your SOC. If you're using your SOC, you're clocking it. So I mentioned earlier the set rate API. I think we probably should have runtime rate calculation be optional. I think that we need a way to deal with this that doesn't explicitly require you to have a large flash footprint to calculate a given rate, to request 12 megahertz, and then have your clock framework figure out what that is. Linux can do that. I frankly don't think we should make that a required feature for every implementation. I think that should be something you can turn on if you don't care about the power consumption and or you want more portability, but I think it should be possible to optimize in the direction. So now let's get into the proposal and how I think we can go about implementing something like this. So first off, just kind of a broad overview of the way I think we could go about this. So I think we can do 2 layers here. So there's first off this clock driver layer. And the idea of the clock driver layer, it's very loosely based on the idea of the common clock framework, which, if you're not familiar, exposes clocks as a kind of object and has fields with different APIs you can call on that clock. And the clocks have their hardware-specific data that's relevant to only them that they use to implement those APIs, things like getting the clock frequency, setting the clock frequency, stuff like that. Clock objects will then also hold references to their parent, which is needed because if you are describing each clock element, and here I mean when I say elements, things like multiplexers, dividers, each of those would be an element. It needs to know what its parent is, to ask its parent what its rate is, and it needs to know what its children are to notify them if there's a reconfiguration event, if the frequency is changing, and it needs to pass that notification downwards. So all of this is good, and this is a way of doing clock drivers, but then there's a management layer. Why does this exist? So this exists because we don't want set rate. We don't want the ability to request a rate to be something that is mandatory, but fundamentally, we need a way to hide driver-specific data from consumers. Consumers shouldn't know which SOC they're running on as far as clocks go. They should be willing to, or a driver should be capable of working across a wide line of SOCs without any knowledge of the underlying clock framework. So the idea that I think we can go with here is kind of similar to pin control, where clock configurations get abstracted to states. There's a high power state, a low power state. And each state has a series of clock nodes that have hardware-specific configuration data as specifiers. So by doing this, you can set up your multipliers and dividers and everything in these states, and then the consumer simply requests, run state, sleep state, and the device tree is where we describe what that actually means. Clock outputs, I think we should still allow them to have their frequency queried directly. That's not something that is nearly as much overhead to implement, and it is a relatively straightforward thing. Everyone needs to know their clock frequency in hertz. Beyond that, this concept of output clock nodes. So we still want the ability to set rate, and I'll describe these more later, but the idea of the output clock node is that we have this hardware-specific specifier data on each clock node, but the output clock node would have a frequency, and that would be your way of saying, I want a frequency rather than a configuration value. And then beyond that, the clock management layer would support rate change callback, so consumers can register for a notification if there's a rate change. So now let's start looking at kind of a little bit of code. So this is the kind of clock driver API that I think we should use. These APIs are things that would only be available within the clock driver layer. So if you remember from the prior slide, there's this management layer and this driver layer. Drivers are all of these individual clock nodes. So clock drivers will use this API to eventually inform the clock management layer about things like the rate that they're running at. So for example, a div might implement get rate by requesting its parent rate and then looking at its register settings to figure out what the output rate of that div is and then return that value. So you have a description here. Notify is kind of our call down from a parent. So notify is how we pass a notification from a parent to a child saying, there's a reconfiguration occurring, you need to deal with it. And you can see that parent rate parameter, that's how we pass down the new rate of the parent. This is kind of like clock recalc rate. If you've looked at the common clock framework before, it's an idea of the parent has changed rate, now the child needs to recalculate its rate, and that will be passed on down through the tree to the leaf nodes that are peripherals generally. Get rate is what it sounds like, reading a clock rate in hertz. Configure, I'll go into what this data is more later, but this is kind of how we actually set a clock's configuration and configure a mux to have a given selection or something like that. Set rate and round rate, these are intended to be optional APIs. So the idea with both of these is that these are the way we handle users who want the ability to request a given frequency for whatever reason. Set rate is what it sounds like, set a rate in hertz. Round rate is relevant because if we're implementing set rate, it's useful to be able to request from a clock node, for the case of like a multiplexer, what that clock node can actually support. So it's useful to ask a clock node, this is the frequency that I'm looking for, what's the closest to that you can actually provide me, so the multiplexer can make the right selection when it's trying to implement that functionality. It's also worth noting that within this, because we have each clock node being represented by a clock structure, that things like external clock generators could be supported with this, since there's no explicit requirement that the clock implementation, that is, the struct clock, be describing something that's on the die versus an off die FPGA or something generating a clock that is then going to get used by the SOC. So then the clock management API. I mentioned this idea of states previously. It's also worth noting that you can have a driver define custom states, because we kind of are going to by default likely define like a run and idle state, but there's more than likely cases, just like pin control, where there's additional states a driver needs to deal with. Beyond this, you can register for notifications, and the idea here, you saw that notify API. We'll go into implementation a little bit later of how this would work, but essentially the clock management API would deal with these notification callbacks as well and forward them out to consumers. Now the API itself that consumers actually see access to, not the clock nodes, but the consumers themselves, is these three APIs. So apply state is kind of our analogous to pin control, where you apply a given clock state, set callback, registers a callback, get rate, gets your rate and frequency. One thing that's worth noting here that I'm open to feedback if we want to try and find a way to support this, but there's no support for explicit runtime rate setting with this. The reason why is because if we explicitly support runtime rate setting, then we're going to have drivers that start to require that. And if that's something we need, we could look at like a kconfig to enforce that requirement or something like that. But in the initial kind of look, I feel like the value of this is that for smaller devices where you want to scale down, or larger devices where you want to scale up, we're not going to end up with a driver that tries to cross that entire range of devices, but somewhere in there says, I want to calculate the frequency I'll need at runtime and then request it, because if you do that, then you've automatically pulled in all of these set rate functionalities that have higher flash impact. So from here, let's start looking at kind of how this device tree would be defined. So the idea here is that we define each node of this clock tree hierarchically. So right here, we're looking at part of the clock tree of an LPC part. There's a clock multiplexer and then a multiplier down here. And the idea here is, right, the multiplier is the child of the multiplexer and can request a rate from it. So the reason we're doing this all hierarchically in device tree is because then we can build that relationship of clocks, struct clock structures, that reference their parents with device tree macros and then can query rate from their parent. And we can, the other way around, have parents notify their children of reconfiguration because this hierarchy is already described for us. So beyond that, let's look at the device tree definition here. So states being defined in device tree, I've mentioned this previously, these kind of specifiers. And what do these actually mean? So these are all hardware specific. That's kind of how we hide, I guess, the hardware specific details. We put them into device tree here. And in this case, right, this was a multiplier or multiplexer and a multiplier. So the multiplexer right there, that's 0, that's in this implementation just a register setting. That's selecting a given input. And then that multiplier value is just, for this specific multiplier, that means pass it through unmodified. But those are all device specific. The idea of this output node I mentioned earlier is sometimes you don't want to go to this level of detail with your SOC, you just want to request a frequency. And going back to this slide, an output node would probably be defined as a child of this multiplier, and it would be responsible for taking in that specifier and dealing with it via the setrate API. So that you wouldn't have to do each individual configuration like this. But the value there is that you have a choice. You have a choice between, okay, I'm willing to accept the flash impacts, I will use this given rate value, versus I want to drill down, save flash, and I'm going to configure each multiplexer and each part of my clock tree individually. And then it's also worth noting, nodes can define additional states if needed beyond just this default and sleep configuration. So now I wanted to look at kind of how we would migrate here and kind of check in to see what is supported and if there's anything we're missing. So clock control get rate, that's a given. We have support for that. It's basically a one-to-one mapping. Set rate, this is one of those. This is something I'm expecting feedback on, to be frank, and I'm interested to discuss how we could deal with this more effectively, because for higher power devices, there may be a need for them to determine what frequency they need at runtime and then request that frequency at runtime. Right now, with this proposal, the way they would do it is they would all have that in device tree, and there's not a way for them to explicitly request that frequency at runtime. So they would use these clock output nodes. Clock control configure is relatively straightforward. This was already kind of passing a void pointer through, and now we would use clock states to define those configuration values and then pass them through to clock drivers. Get status and async on. So both of these, I think we can probably handle via the callbacks, because what you're interested in is the status of your clock, and we can pass that down via this notify API, in particular async on. If you're looking to see when a clock turned on, then you can call this, you can wait for a callback to say its rate has gone from 0 to not 0. The clock is now on. Clock control on and off both, I think, can be dealt with via these clock states. This idea of now a gate is described as a clock node with a 1 or a 0 to say this is going to be on or this is going to be off in this configuration. So now let's look a little bit at how the framework would be implemented and what that would look like. So I wanted to just quickly walk through how these nodes would be implemented to give you an idea of the implementation for one of these node drivers. So this is for a divider, and the way this works is relatively simple. It requests the rate from its parent node. It looks at the divider setting in a register, and then it divides and returns that value, looking at configure. So configure is kind of the meteor API here. This void pointer, I've kind of been dancing around it. Where this comes from is it's that specifier value. So that specifier value on the node gets passed into this function when you go to apply a state. So jumping back a few slides real quick just to try and link this up, that specifier value, that 0, is what gets passed into configure. And then you take that value, cast it to what your driver knows it is, and you apply it. So this allows you to deal with, a divider, obviously that's probably one value. A PLL is going to have more than one specifier. There's going to be quite a few specifiers to configure something like that. And then this clock notify children call. So what that is notifying children of the clock reconfiguration is about to occur. And this is necessary because say you're dealing with something like a flash, I guess, SOC flash, where you have wait states. It needs to deal with and increase the number of wait states prior to the clock frequency rising. So this notification will occur before settings get applied so that any consumer can deal with a rate change before there'd be a crash from the clock frequency increasing or something like that. And then notify. So notify is generally a simple implementation. You take in your parent rate. Looks a lot like, honestly, the get rate implementation. You take in your parent rate, you calculate the new rate, you pass that on down. And this is worth being noted. This would be called from the parent clock, and we propagating downwards. So now how do we implement the subsystem? So I mentioned in the last slide how we're going to pass these values through, these specifiers through. These macros are what we use to actually extract those values. So these kind of look like what you see in pen control. The big difference here is we use the compatible to determine what the macro name will be, and then your SOC, or if you have an external clock producer, you'd have to provide a header file with these macros in it, but you would provide these macros, and then the clock framework uses those macros to extract what the configuration values it needs to pass through would be. And then we configure set points with this clock configure API. So, I've mentioned the concept of the output clock node with this frequency before. That one is kind of the oddball case, but the way that would be done, right, is that you take your given configuration setting, which in this case is just a frequency, and instead of configuring some multiplexer register value or anything like that, you just call the clock set rate API on the parent clock, and that's how you apply your given frequency. From there, how do we implement clock callbacks? So I said there's kind of these two layers. What I think we can do is we can define kind of a minimal clock structure for the consumer node, whether that be a UART, an I2C, whatever peripheral it is, and that clock structure implements the same notify API as all the other clock structures, right? So the infrastructure is the exact same, but that callback, as it goes down, the handler for the notify API at that level just forwards the callback to the consumer. So that's how you hook that in. So now I kind of wanted to go over the current status of this implementation. So I have a basic implementation completed for the 55S69, which is why I keep referencing its clock tree all over this presentation. We can configure the clock tree to run a basic Hello World application. The main issue I am still trying to figure out is flash. So currently, it's about a kilobyte of additional flash to do this framework with the notification callbacks. If we turned that off, because for a case where you don't care about power management, you're likely setting up clocks once, we get it down to about 300K of additional flash versus using the clock control framework, but there still is a flash impact. RAM in both cases is negligible. I think less than, I think it's less than 100 bytes, but it's significantly less impact. Beyond that, there will be an RFC for this. I just need to complete the set rate and rounding implementation to validate that they can actually function and then put documentation together. I also wanted to cover a couple of alternative options before I open it up to questions. One thing I explored for this was using this concept of these set point and states in an SOC-specific manner, so something like very adjacent to pen control, where there is one singleton driver that handles the clock state application, and that's what you have for your SOC. One big problem with this is you can't have off-chip clock producers. Another issue with this is your code reuse is pretty minimal. But there is an RFC for that approach if you'd like to look at how that was done. We could also implement this using the current clock control subsystem. The main concern I have for this is if we want to do that child-to-parent reference, which I was describing earlier, which I think is crucial to actually generate these callbacks. Device structs are kind of big, y'all. Like, compared to this clock structure, which is 3 pointers, if you have like 25 clocks in your tree, which for the basic hello world example, I do, it's like 100 bytes per, it's a lot of flash. So that's why I think we probably need something different here, because when you have this many nodes, it gets expensive. Additionally, there's the concept of the set_rate API, which I am still of the opinion that we should probably try to avoid requiring that for every base image, because smaller parts just don't need to calculate their entire clock tree at runtime like that. And then beyond that, every extra API field, you'll notice there's not that many APIs in the clock driver implementation. That's because those also add to flash usage. And then there's no facility for rate change callbacks. So that concludes the presentation. We've got about 10 minutes for questions, which is a little less than intended, I'm sorry. But yeah, who would like to go first? The anticipation is killing the bricks. Sure.
Oh, hello.
Oh, or that.
Thank you for your presentation here.
Sure.
Did you consider the use case of like in power management, where you can actually say this device is busy? So if you have ongoing transactions, for instance,
I likely can't change the clock right now. Please don't.
Please
yeah,
don't.
So this is, I mean, I have thought about this. I want to give credit to Erwin, because I talked to him about this a couple days ago, and he asked me that, and then I thought. But I didn't screw with the slides because I'd already uploaded them. So I think we could do this via the Notify API. My idea is, right, we're propagating down to children, and there's a return code. We could make the return code say, hey, I'm busy, and then that just propagates all the way up. Because you call this Notify Children, jumping back many slides, you call this here. If that returned an error code, you just wouldn't apply, right? Something like that. Another thing which I assume someone will ask about, because I've been trying to figure it out too, is the idea of how to deal with a situation where you have just changed your mux to select a different source, and now you no longer need that PLL you were previously very interested in. This one I'm not sure on, I will be honest. My best idea right now is to also use the return code of Notify Children and look at that. But the problem with that is that if you reconfigure, you have to then do another configuration call on your PLL to find out that you aren't using the child. You're raising your hand. Do you have a better idea? Because I'm interested.
So I was thinking about that exact
Yeah.
thing. I previously did a power management system for Kinetis, which I think you know well, and the complexities of it. And in that case, what we were doing is we're basically putting a ref count.
Yes.
And so by using a ref count, say on the PLL, on at the different, I don't know if it's at the different points of the mux, or
But yeah, using a ref count,
something
sure.
along those lines.
No, I think a ref count, I mean, I'll be honest, I'd like to use a ref count too. The reason I didn't go with it right now, there's a few. One is that, again, Flash, if you add an API to tell the parent, decrease your ref count, you've just added an API for everything. The other thing is actually, again, cursed Flash optimizations, there's no, let me see if I have a backup slide with the struct clock in it. I've turned this off, that was a not wise choice. Okay, there's no backup slide. That's fine. The clock structure, as it stands, only has one pointer to a device-specific hardware data, because usually you only need ROM data for like a mux or a div, and you only really need RAM data for something like a PLL. So there's kind of that problem that if you start putting a ref count and everything, yeah, I mean, that is something I'm aware of. The other thing I thought about for this is something like using maybe a power management like framework to do it. But again, you have the problem of anything more in this clock structure is additional flash. Yeah, I'm still trying to figure out the best way to do it. It's worth noting if you're willing to use this method where you explicitly reference each device in your set points, then it's very easy. You just say, oh, my PLL doesn't need to be on anymore. Please turn it off. But that doesn't solve everyone's use case, right? That doesn't solve the use case where you just want to request a given frequency.
It also doesn't solve the problem of you want to be able to drop to, say, a different low power state. Like, again, with the Kinetis, all the different low, you can only go to this low power state if these peripherals are off.
Yes, yeah, there's transitions.
It ties into clocks and other things, but that it doesn't play well into that either. So.
Yeah.
Did you consider so we were talking about device frequencies here. Did you consider to extend, or will it allow to play with core frequency as well, to do some frequency scaling, to enable frequency scaling?
To enable like dynamic frequency scaling or something like that? I think, yeah, yeah, because then you have, I mean, with this, you could accomplish that provided you knew what your target frequencies were at runtime, because you could set them with these clock output nodes. But no, I haven't dove into it that deeply. I think it superficially probably would be something you could do with this.
Because one of the issues in frequency scaling is that you have to inform everyone that your bus clocks have changed. So
yes, yeah, and
so
that's
this
what these.
you're adding a part of you're solving a part of this issue. And it would be interesting to see what are the missing bits to enable the frequency scaling.
Sure, yeah. I mean, you should, with this framework, if you request a new frequency for your core clock and you have to change muxes to achieve that or something, notifications will propagate down. So other consumers would be aware that their bus clock has changed or something like that, because they'd each be subscribed to a notification for it. But yeah, no, if we did something like this, it would be interesting to see what comes out of it. And I want to be clear, it should be obvious at this point, I don't have all the answers, right? This has to be a group effort to figure out what we can do.
On one other point that we discussed is that maybe, so at one point you are quite close to power domain here.
Yes,
so maybe it would be interesting to see
if we could use a power domain here. Yeah,
yes,
no, that was something I was thinking about as well after you mentioned it. I mean, potentially, the thing that I think we really need to figure out is how we can. The main thing I still don't have a great answer for is the question you asked, like, how do we deal with a situation where we want to power down a root node because it's no longer used? Because a ref count is obviously the simplest solution, but are we okay with the flash impact of an additional API to say I'm no longer using this, and then yet another thing in the RAM to track that ref count for each node? Yeah, and that's an open question. We may very well be, right? So, yeah.
But anyway, it's quite interesting, quite good progress. Thank you.
Absolutely.
So, I mean, there was being able to describe everything in device tree. Were you able to, at build time, basically validate that your clock tree, description was valid for because right? I mean, you go and like.
And that's a very good question, a good concern. No, I don't have. Currently, there's not. The validation that could be done would be something where your PLL, when you go to request a frequency or something like that, would say, no, this isn't something I can support. And that would be relatively easy to implement, but we couldn't do it at build time. I'll be honest, I think part of the way to do this at build time is to offload that type of clock configuration to some type of solver, right? I'm not sure what that looks like, but for embedded devices, often the way that you configure, I know NXP supplies something like this, where you say, here's my clock tree, here's what I want it to look like, spit out C code. I think we probably want solvers that look similar enough to do that kind of setting up muxes and configuration and validating that at I guess before even compile time. Are we out on time?
Yep.
Okay. Well, if anyone wants to talk in the hall, I'll be available.